So yesterday I was watching one of MIT's open courseware videos on differential equations, and I came across an example that was actually pretty interesting, which is rare in a math course. This is from the Differential Equations 18.03 Spring 2006 lecture. All credit goes to Arthur Mattock, who taught the class. And this example is about modeling a relationship in the show Seinfeld. Now, before I saw this example, I didn't really know anything about Seinfeld. I never watched it, never was really interested. This relationship that he modeled was between George and Susan. Susan apparently died from being poisoned by licking an envelope, which was strange, but the way he modeled it was he gave two equations, x prime and y prime. And I'll write out the equations and explain what they represent afterwards. So x plus 2y and y prime is equal to negative x minus y. So what do x and y represent? X represents Susan's love in the relationship, and y represents George's love. I'll write this out. So x equals Susan's. X equals Susan's love. Y equals George's love. Now, this isn't some magnitude of love. Well, I guess it is, but what x and y actually represent is the deviation from their normal relationship. So x equals 0 and y equals 0 would represent their normal relationship. I assume that since they're in a relationship in the first place, they must like each other somewhat. So x and y both represent a normal amount of affection for each other, and consequently a positive x prime would indicate that Susan's love for George is growing stronger, and a negative x prime would mean that she is growing more and more distant from George. And same goes for George's y equation. Now, what do these equations physically represent? Well, we see that in Susan's equation, there is a factor of x right here. What does that mean? Well, it means that as Susan, the more Susan loves George, the more she tends to love him even more, which I don't know how much real sense that makes. I guess that's true in some sense. And there's also a factor of y here, which means as George loves her more, Susan gets more and more happy and loves him even more. Now, George is the opposite. The more and more Susan loves him, the more he grows more distant from her, and he loves her less because of that. Now, I guess the way he explained it was because George is neurotic, and he gets scared whenever people get close to him. So this is what this negative x means, and there is also a y, which means that the less George loves Susan, the more scared he gets, so he reverses that trend. Now, in other words, if George is liking Susan above normal, he gets scared, and then his rate of change of love will go down, which is an interesting character that makes him. So I guess that gives you an idea of what neurotic means. But these are our two equations. These two equations make a linearly coupled system of linear equations. I guess I said linear twice, so that was redundant. But now we can move on to solving it. I'll erase these two. Assume that you remember what these two x and y mean. Now we can start solving it. Well, we can first write this. I always like to derive it from the beginning, so I make sure that I know where I get all my equations from. So we can write the coefficient matrix and x and y. Now these two are equivalent, and we can make our educated guess that xy is of the form a b e to the lambda t. This is our eigenvalue. This is our eigenvector. Now if we have this guess and we plug it in, I'll skip some steps. What you end up getting is lambda AB equals 1, 2, negative 1, negative 1 AB. That's what you end up getting. I'll erase our guess. This is unnecessary from now on. Now we have this form, we can rewrite it in the form our coefficient matrix stays on the right. Well, I guess we switched the right and left, but this turns out to be minus lambda. Remember that we can't subtract a scalar from a matrix, so we multiply by its identity matrix. And on the outside is our eigenvector, and this would all equal 0. Now we find the values of lambda for which there is this equation has a non-trivial solution. Now this would mean the determinant of 1, and we would subtract lambda from the diagonal because of the identity matrix. Negative 1 to negative 1 minus lambda. And we want this determinant to be equal to 0. Now our determinant, I don't want to do all the algebra. I'll just write out what you get at the very end. You get lambda squared plus 1 equals 0. And this makes our eigenvalues, plus and minus I. I'll actually write this at the bottom. I'll need more room for the rest of the problem. So lambda equals plus and minus I. Wrong tool. I'll clear this off. Should I clear this? Yeah, I'll clear it. Now, if you didn't write it down, our A matrix turned into 1 minus lambda, negative 1 minus lambda, and negative 1 and 2. We also had this AB, and we had this equal to 0. This is what we got after evaluating that expression. Now that we have our lambda values, we can plug I in for lambda. Now note that we only need to put I or negative I as our trial solution. Putting in both would just give us a redundant solution, and it wouldn't do us any good because the negative in the factor would just be absorbed in the constant. Now we'll say lambda I, actually, I'll make this a different color, make it exciting. Lambda equals I. Now what do we get? We get 1 minus I, 2, negative 1 minus lambda, times the matrix, the vector AB equals 0. Now we can just assume that A equals 1 to get our eigenvectors, and we will get, actually eigenvector in this case, we will get AB equals, if we assume a equals 1, we will get I minus 1 over 2 for our b value. This will satisfy both the top and bottom over here. Now, we don't want to leave this AB vector in this form. Now, how do we rewrite it? We want to separate the real and imaginary components. I'll put it down here. AB equals, let's do the real part first. Our real part would be 1, and we have a negative 1/2 real part, right? And we can do our imaginary part next. There's no imaginary part on the top. We'll put 0, and on the bottom we'll put 1/2. This is our AB vector separated into its real and imaginary components. Now remember what this AB value was being multiplied with. This AB value in our original guess for our solution, we defined xy as being a b e to the lambda t. Now that we have our ab and we have our e to the lambda t, we said that lambda was equal to I. Now we can make that into a cosine and sine function, right? I'll write that down here. We say that xy is equal to, guess I'll write it out, 1 negative 1/2 plus I 0 1/2 times cosine of t plus I sine of t. Now this is actually our solution. There is, I guess we're not done yet, actually. We want to take the real component of this. Guess I didn't leave myself very much room. I will create another section, I suppose. It's not much room, but it'll have to do. Get xy is equal to, if we multiply it out, we get 1 negative 1/2 cosine of t, and the i's cancel in the second part, and we get minus 0, so 1/2 on the bottom. 0 1/2 sine of t. Now this is our final xy solution. Now what is so interesting about this solution? Well, let me make some more room and I'll explain. You've probably already figured it out, but I'll just make sure you understand what just happened here. The solution I found to be very interesting. Now, if we expand it out into normal form, we get x equals cosine of t and y equals negative 1/2 cosine of t minus 1/2 sine of t. Now this bottom expression is actually sinusoidal as well. Now what does this tell us? Well, it tells us that their love, if we graphed it, would simply fluctuate back and forth, which is surprising. When I first saw this problem, I assumed that one of them would get tired of the other and they would veer off at a exponential rate. But if we actually graph this, we're given the x and y values, so we can graph this. This is very simple. We would actually get a ellipse, and they would be traveling around as time goes on. So this is just a infinite circle of love, which I found to be very amusing. This is also a very good demonstration of how to find solutions of complex eigenvalues. So this benefit is twofold. You got an interesting example as well as a practical example. So that's it, I guess. Thanks for watching.